Data required for earthing system sizing calculations. One is soil earth resistivity. It is obtained from site data, length of the electrode and dia of the electrode. These are obtained from the earthing specifications. This is 3000 mm, 65 mm. Here the dimensions are considered in centimeters. This is soil resistivity in ohm meter. Length of the earth strip 75 by 10, approximately 300 meter. Length of 50 by 6 earth strip in meters, approximately 600 meters. Width of the earth strip, it's 75. In centimeters, 7.5. Width of the earth strip, 50 in centimeters, 5 centimeters. Depth of burial, the earth strips are buried in at 500 mm. In centimeters, 50 centimeters. System fault level, this is calculated in kiloamperes. Operating time of protective devices, either 1 second or 3 seconds. And factors from IS 3043. This is for safe area. For hazardous area, these two factors obtained from IS 3043. Coming to corrosion factor, we have to consider 1% corrosion factor for 20 years. After 20 years, this total network has to be dismantled and a new earthing network shall be prepared. The total 20% we are considering 1.2, and design margin or safety factor 50% design margin or safety factor is considered. So after preparing this total earthing network, the earthing network is suitable for dissipating 62.91 kiloampere plus this design margin. That means approximately my network is suitable for dissipating 100 kiloampere of fault current, even though fault current is 62.9 kiloampere. Why? Because we have considered this design margin and corrosion factors and other factors. So this is the method of designing earthing network. Now we will see fault current calculations based on MVA method. Coming to earthing system sizing calculations or design calculations. For that, first we required fault current. So this is about fault current calculation. Here we are considering motor and generator. These two are connected to 415 volt bus, and this is 11 kV by 415 volt transformer. These two are separate buses. Cable data, only R and X data is considered, and this is 11 kV board, where the maximum fault current of this 11 kV board is 40 kiloampere. Here the approximate X by R ratio considered is 15. This is 11 kV board, 1250 ampere. Maximum fault current capacity is 40 kiloampere. This can be considered as a lump network. Here we can do calculations in two ways. One, if we know the short circuit MVA of this lump network, or if we know the fault current of this network at this bus, then we can also calculate the short circuit MVA. So here we are considering that fault current is given 40 kiloampere and short circuit MVA is calculated based on this. This is the formula to calculate the short circuit MVA if we know the fault current. VL is the line voltage, IF is the fault current. Fault current we know, so the short circuit MVA is 762. Coming to cable, in case of cables, we know the impedance data. So the short circuit MVA can be calculated if the impedance value is known. The line voltage is already known, 11 kV. kV square divided by the cable impedance, short circuit MVA. This is for cable 1 and this is for cable 2. These two cables are running in parallel. Coming to short circuit MVA of transformer. In case of transformer, the MVA is known and the impedance is also known. So from this short circuit MVA formula, MVA divided by impedance, we can get short circuit MVA. This is for transformer 1 and this is for transformer 2. For machines, the short circuit MVA can be calculated by this formula, the MVA divided by XD double dash. For motor, the XD double dash is approximately 15% and MVA is 1. For generator, the MVA is 1 and XDI double dash is approximately 16%. So there is a slight variation in the short circuit MVA calculation. This is 6.25 for DG. This is 6.67 for motor. This is because XD double dash is slightly varied. So the short circuit MVA for all the elements is calculated for lump network, for cable, for transformers, for machines is calculated. After that, we are assuming a fault at this bus, and so we have to minimize this MVA network to this faulted bus. So the MVA network is similar to capacitive network. Minimization of capacitor network, similar formulas shall be followed for the MVA network also. Coming to network minimization, these two buses are not connected here. So these two MVAs are in series. In series means then we have to take the elements connected in like parallel in case of resistor. So the net value is lesser than the minimum value. Out of these two values, the minimum value is 20. Then the net value is lesser than 20. These are the actual values. The same case for this also. And after this, these two are in parallel. That equals to resistance in series. 17 plus 17 nearly 34. Coming to machines part, these two MVAs are connected in parallel. In parallel, these two are on same bus. That means these two can be added. 6 plus 6 around 12. This network is simplified from the previous sheet. The grid short circuit MVA is 762 and the cables and transformers network is simplified. The final net MVA is 34.3. Machines short circuit MVA is simplified and it is 12.9. Our fault is on load bus. We have to simplify the MVAs which are above this bus. So 34.3 MVA and 762 MVA, these two are connected in series. Series means equal to parallel. In parallel, net value is lesser than the minimum value. Out of these two, the minimum value is 34.3, means 32.8. So at this fault bus, finally we have two MVAs. These two MVAs are in parallel. In parallel means we have to take the series formula 32.8 and 12.9 equals to 45.76. This is our final short circuit MVA at the faulted bus. So finally, at the fault bus, we have calculated the short circuit MVA and line voltage is known 415 volt. The fault current we need to calculate. The fault occurs on this bus. What may be the maximum fault current? In this case, the maximum fault current can be 62.91 kiloampere. This is our system fault current. This is another case where DC is feeding directly a motor, the source impedance, and this is cable impedance, and this is cable data. 2 runs 3-core 240 cable, total length is 300 meter, resistance of cable, inductance of the cable, and if there is a fault at motor terminals, what may be the maximum fault current. Similar to previous case, the fault short circuit MVA is calculated for DG, for cable, and for motor is calculated. The network is simplified. After obtaining the short circuit MVA, the fault current can be calculated. In this case, 10.14. Variation in earth strip size. For connecting the same equipment neutral to the earthing network of the same equipment's body to the earthing network. For example, if the load current of the equipment is 400 amperes, then neutral current will be 200 amperes, body current will be 100 amperes. Neutral current is more than enclosure current. For this reason only, earth strip size of neutral is more than earth strip size of enclosure. Size of neutral earth strip is more than size of enclosure earth strip. These are the recommended earth distance values to be maintained at various locations. CPP switchyards nearly 0.5 ohms. For EHV substations up to 1 ohm, HV substations up to 2 ohm. Other cases maximum up to 5 ohms. In case of towers, lightning arresters, we can go for maximum 10 ohms. Electrode earth resistance value depends upon length and dia. If we double the length of the electrode, then the resistance value can be improved up to 40%. If we double the dia of the electrode but not the length of the electrode, in this case we can improve only 10% of earth resistance value of the electrode. So the better choice is increasing the length of the electrode we can improve the earth resistance value of the electrode. Range of soil resistivity and class of soil and the elements to be considered in sizing calculations will be as per this table. If the soil resistivity is less than 25 ohm meter, then the soil is severely corrosive. For this, we have to take 30% of allowance. For the range 25 to 50 ohm meter, this is moderately corrosive, 15% is sufficient. For 50 to 100 ohm meter, this is mildly corrosive, 15% allowance is sufficient. For more than 100 ohm meter, very mildly corrosive, no allowance is required. It means soil has to be very low resistive in order to have better resistance values. We can go for water dipper or water drop line for each earth pit, and it improves the soil resistivity and it improves earth resistance value. Steel material get corrode 6 times faster than the copper material. These are the formulas for calculating the earth resistance value of each earth electrode as per IS 3043. Here L is the length of the electrode in centimeters, A is the dia of the electrode in centimeters, rho is the soil resistivity in ohm meter. This data is required to calculate the earth resistance value per earth electrode. Resistance of earth strip, rho is the soil resistivity in ohm meter, L is the length of the earth strip in centimeter, W depth of the burial, E is the width of the earth strip, units in centimeter and centimeter. Calculating the maximum surface current density of earth electrode. Rho is soil resistivity in ohm meter, E is fault clearing time in seconds, J is maximum current density of the electrode, amps per square meter. This formula is for calculating the cross-sectional area of earthing conductor. This is for dissipation of fault current. I means fault current, S means cross-sectional area, mm square, T is fault clearing time in seconds, K is factor. Calculate the K, use this formula, and this is data. So we use these formulas for calculations: cross-sectional area, current density of the electrode, resistance of earth strip, and resistance of earth electrode. After gathering all these data and calculating these fault currents, we have to move to sizing calculation sheet. By using these formulas and those data, we can complete the earthing system sizing calculations. These are the earth electrodes, these are the earth strips. Our first step is surface area of the earth electrode. This is length, this is dia, and this is pi. From this, we can calculate the surface area of the earth electrode in square meters, that is 0.61. Step 2, here we can calculate the maximum surface current density of the earth electrode with reference to soil resistivity. This can be directly calculated from this formula. Our final value is amps per square meter. This is the maximum surface current density of electrode per square meter. That means if the earth electrode's surface area is 1 square meter, then it can carry 1700 amperes. But our earth electrode size is 65 dia, 3000 mm long. From that calculations, square meter surface area of that electrode is only 0.61. So fault current capacity of our selected electrode is obtained. This is fault current capacity of one earth electrode. Fourth step, we already know that our fault current IF around 62 kiloampere. From the calculations, one earth electrode is able to dissipate approximately 1 kiloampere, which is slightly more than 1 kiloampere. Then to dissipate 60 kiloampere fault current, how many number of earth electrodes are required? Approximately 60. From the calculations, the number of earth electrodes required to dissipate the total fault current is 58. Fifth step, surface area of one earth electrode is 0.61. Then the total surface area of 58 number of earth electrodes. This is 35.53 square meters. 35.53 square meters of surface area required to dissipate the total fault current. So from this total required surface area of earth electrodes, 10% has to be deducted due to the perforation. Finally, 30.20 is the total surface area of the earth electrodes. In these earth electrodes, corrosion factor and safety factor not considered, then this is the total surface area of the earth electrodes. In case of earth electrodes, we have calculated the required surface area. In case of earth strips, we have to calculate the required cross-sectional area of the earthing conductor. These are the calculations for safe area, and these are the calculations for hazardous area. In case of safe area, we are considering 75 by 10 earth strip and 50 by 6 earth strip also. 75 by 10 equals to 750 square mm. 50 by 6 equals to 300 square mm. This is surface area of the provided earth strips. To calculate the cross-sectional area, we use this formula I into root T by K. K value obtained from the table. By using that formula, finally we calculate this cross-sectional area in square mm. After considering corrosion factor and safety factors from the table, corrosion factor is 1.2, whereas safety factor is 1.5. The final cross-sectional area is this. Similarly, in case of hazardous area, the required cross-sectional area is this much from the formula. After considering the corrosion factor and safety factor, this is the required cross-sectional area. But from 75 by 10 earth strip, the cross-sectional area is 750. From 50 by 6, the cross-sectional area is 300. So 2000 divided by 750, approximately 3 runs. 2000 divided by 300, approximately 7 runs. So by providing these many runs of earth strips, we can dissipate those fault currents. So 2 runs of 75 by 10 earth strip is required, or 5 runs of 50 by 6 earth strip is required. Here one question arises of what length it is required. For this, here we have to take some approximation. From this calculation, the total required surface area is 35.53. If we have this much surface area, then the total fault current 65 kiloampere or 62 kiloampere can be dissipated. So the same surface area we are taking here as a reference, 35.53 square meters surface area will dissipate 65 kiloampere or 62 kiloampere. Then the length of the earth strip required and the dimensions of the earth strip. From this calculation, we can obtain the total length of the earth strip. Here length is unknown in meters, which is unknown. From the earth strip, the dimensions can be calculated. 75 plus 10 into 2. This is of 1 earth strip into 2 or 2 earth strips or 2 runs. This is also we have to consider in meters. This we have to match with 35.53 square meters. From this calculation, we can get the length value. So here from this dimensions, this becomes total 0.34 meter. Dividing this 35.53 with 0.34, we get total length of 105 meter. That means if we have 2 runs of 75 by 10 earth strip of 105 meter, then we can have 35.53 square meters of surface area. That is sufficient to dissipate 62 kiloamperes of fault current. Similar type of calculations can be done for 50 by 6 earth strips for 5 runs. Similar calculations are repeated for this unit area also. For 3 runs of 75 by 10, what may be the length required? For 7 runs of 50 by 6, what may be the length required? That means only 2 runs of 75 by 10 earth strip of 105 meter. This only material can dissipate total 65 kiloampere of fault current. Similarly, other cases we can calculate But from the given data, we have considered total length of 75 by 10 and total length of 50 by 6 earth strips as 300 meter and 600 meter. Based on this, we have to calculate the surface area. Based on those lengths, 300 meter or 600 meter, we have calculated the surface area in square meters. This is 75 by 10. This is for 50 by 6. This is the surface area we have calculated. The surface area is calculated 300 into 0.17, which is 75 plus 10 plus 75 and plus 10. This is total surface area minus 15% of this area due to perforation we have to consider. Similarly, in 50 by 6, 50 plus 6 plus 50 plus 6, that is 112. So 0.112 into 600, the total surface area minus 15%. The final values are these values. So the total surface area provided by 75 by 10 earth strip and the total surface area provided by 50 by 6 earth strip and the total surface area provided by earth electrodes, all these are parts of complete earth grid, earthing network. The required surface area 35.53 square meters is sufficient to dissipate 62 kiloamperes of fault current. But we have earth electrodes, earth strips of various sizes in the earthing network. If there is any fault in the system of around 62 kiloampere, the total fault current can be easily dissipated. The provided surface area of the earthing network is more than the required value. The required value is 35, but the provided value is 130, which is approximately 4 times. Coming to earthing resistance calculation for earth electrode, for earth strips, and for total earthing grid. This is the earthing resistance for earth electrode. For this, we will be using this formula. In this formula, ρ is the soil resistivity, L is the length of the earth electrode, T is the dia of the earth electrode. The values from the table, length of the earth electrode, dia of the earth electrode, and ρ, all these values are substituted in this formula, and finally we get this value, approximately 5 ohms. This is the earth resistance value for earth electrode. Total number of earth electrode to dissipate the fault current 62 kiloampere. We have total number of earth electrodes as 58. All the earth electrodes are connected in parallel. So net resistance value, if we consider only the earth electrodes, then 5 divided by 58. Approximately the net resistance value of all earth electrodes will be 0.086. In this case, we have not considered earth resistance value of earth strips. Similarly, earth resistance value of earth strip for 75 by 10 and 50 by 6 can be calculated by using this formula. ρ is the soil resistivity, L is the total length of the earth strip, W is the depth of the earth strip, T is the width of the earth strip. All the data obtained from this table. Depth of the earth strip W, width of the earth strip, length of the earth strip, all this data obtained from this table and included in this formula. Finally, we get these values. This is the value for total length of the earth strip. This is the value for the total length of the earth strip. This is of 75 by 10. This is of 50 by 6. This is the net resistance of earth electrodes. This is the net resistance of earth strip of 75 by 10. This is the net resistance of earth strip 50 by 6. In the network, all the resistors are in parallel. So the net resistance, final resistance, which is network resistance, is parallel value of all these three, that equals to 0.03 ohm. So the network must have very low value compared to individual values. So these are the total calculations of earthing network.